Okay, so last time we talked about predicates, and also we began discussing how to negate a quantified expression, quantified predicate. So it's a propositional function or a predicate. It becomes a proposition when we give values to the variables. Okay, and quantifiers actually give a predicate values, a range of values, right? Or it just makes a more general statement about the predicate. So there is a universal quantifier. When we want to make a statement like that, this predicate P is true for all values in the universe of discourse, we say for all x P of x, right? And when we want to make a statement that this predicate is true for at least one value or for some values in the universe of discourse, then we say that there exists P of x, right? We make this statement. And now we know for all x P of x is true when P is indeed true for all values of in the universe of discourse, and there exists x P of x is true when P is true for at least one value, right? So we know when is it false, when is it true, and so it becomes a proposition, and now we can make other propositions out of them. We can negate them, we can AND them, we can take their conjunction, disjunction, negation, and many other things. Okay. So a quantified predicate is a proposition, so we can negate it, and this negation will also be a proposition, and the negation of a quantified statement will be true if and only if the negation will be true if and only if the original expression is false. Okay, and so we know what negation is, right? So we started to talk about this. Suppose our universe of discourse is students in this class, students who are registered in the current offering of discrete mathematics, and we have this policy that calculus is a prerequisite of discrete mathematics. So anybody who is registered in calculus registered in discrete math must have taken discrete calculus beforehand. So we can say that for all x C of x, right? So if you want to negate this statement, what would be the negation of this? In English, every student in this class has taken calculus. What would be the negation of this? A statement which will be true only when this is false and false when this is true. Okay, totally opposite statement. That statement that cannot be simultaneously true and false with this one. Okay, so can you make the statement? Yes.
There are some students who have not taken calculus.
Okay, so last time, if you remember, some of you said that no student has taken calculus, right? So no student has taken calculus, and everyone in this class has taken calculus can both be simultaneously false. Yes, if 3 of you have taken calculus, the rest 97 have not taken calculus, the statement is false that everybody has taken calculus because these 3 have not taken calculus. And this statement is also false that no one has taken calculus because these 3 have taken calculus, right? So it cannot be the negation of it. Okay, the negation will be that no, it is not the case that everybody has taken discrete calculus, right? Yes, please. Go ahead. Not every student has taken calculus seems to be correct depending on how do you do this, the English thing. The thing what I said was not correct is that no student has taken calculus. That means like the number of students who has taken calculus is 0. Right? What you said is that it is not the case. Suppose the class has 100 students. You just said it is not true that all 100 of them have taken calculus. Right? So that's a correct translation perhaps. It is not the case that every student in this class has taken. So there is some student who has not taken calculus, and only one will give me is actually good enough to make the statement, the negative of the statement. Yes, please. Yes, we can say that at least one student has not taken calculus. There exists at least one student for which the blue statement is not true, right? For which this predicate is not true, has taken calculus. Okay, so then we derived a journal kind of form of this thing. Generally, if you have a universally quantified statement for all x P of x, The negation of this would be there exists x not p of x, right? Now you think of whatever way you want to understand this. So now you can just make up a story in your head whatever way you want to understand this. The best way is a programming way. If you have a if a and b and c and d, four conditions, and then there is else condition. When will the else statement be executed? When the and of four predicates is false, then it will be considered. And when is the and of these four predicates false? When at least one of them is false, right? Or that's the other story. If you are going to, with this example, suppose there are 140 students in this class. When is the statement true? When each and every of these 140 people have taken this calculus. And if there is one person or two people or seven people or 139 people or 140 people who have not taken calculus, what happens to this course, right? So make a statement, try to translate it, try to negate it, then retranslate it back and make sure it makes, you need a lot of practice with these things, and we are going to give you a lot of practice as examples here in the in-class problems and your practice problem sets and homeworks, and hopefully in the exams and long quizzes you will see many more examples. Okay, so this was the other example. These are the things we discussed briefly. So we discussed in quite detail. So I'm going to just review it because I'm going to build upon them and make a general story. The next thing, an existential quantified statement. Some student in this class has taken chemistry. Assume it is true, right? We know it's true. Somebody has taken chemistry, maybe many of them. When will this statement be false? Or make the negative statement of it. Make the statement which is the negation of this. Okay? Yes, go ahead. None of the student in this class has taken chemistry. Any other attempt? Every student has not taken chemistry. Okay, this is a rewording of the same English sentence. Any other way to write? Yes. There is a student in the class who has not taken chemistry. There is no calculus. We are talking about chemistry. So there is a student in the class who has not taken chemistry. That's a very good attempt because that's going to make our concepts clear. Again, suppose there are 100 people in there, 140 people in this class. Okay, suppose the first 40, whatever first 40 means, have taken chemistry, and the last 40s have not taken chemistry. Okay, what happens to the middle? The middle are currently taking chemistry. Okay, is this clear? So 40 plus some number, 80 I guess, right? So those 80 are currently taking chemistry, 40s have taken chemistry, and 40s have not taken chemistry. They will never take chemistry. Okay? Now look at the blue statement. Is the blue statement true in this setup of the class when 40s have taken chemistry? Yes? Now the red statement, which is that some student in this class has not taken chemistry, is that also true? Because those 40s have not taken chemistry. That is also true, right? So some student has taken chemistry, some student has not taken chemistry cannot be the negation of each other because they are simultaneously true for the same universe of discourse, right? We are talking about one same set of students. For them, both are true, so they cannot be the negative of each other. On the other hand, the two other attempts that we got were that no one has taken chemistry, right? Or everyone, so I checked the transcripts of everyone and I didn't find anyone having taken chemistry, right? That's kind of one other translation we got. That cannot be true simultaneously with the blue statement in all scenarios. Anybody taken chemistry, all of them taken chemistry, some have taken chemistry, just do this, play this game, just make a table of 100 students, how many have taken chemistry, there are a few cases, right? Greater than 0, equal to 0, or equal to 140, less than 140, those kind of, just do those case analysis and see that in no scenario will both the blue statement and the green statement that no student has taken chemistry are simultaneously true or simultaneously false. Okay, they are really the opposite of each other. Generally speaking, so I just said, so here's the number of people who've taken chemistry. What are the possible numbers? In terms of predicates and their truth value, possible number is 0. Cannot be negative, right? The number of people who have not taken chemistry, who have taken chemistry cannot be negative 17, right? So 0, greater than 0 but less than 140, and equal to 140. Cannot be even greater than 140, right? So these are the three possible cases. In all cases, you see that the red statement, somebody has taken chemistry. The red statement, no one has taken chemistry, cannot be simultaneously true or false. In all of these three cases I just said, okay? Okay, so this is basically the De Morgan's law, and this is not that we stopped here. Look at this. The De Morgan's law said that the negation of OR of two proposition is equal to the AND of the negation of in the individual propositions, right? Not of P and Q is equal to not of P or not of Q. And not of P or Q is equal to not of P and not of Q, right? Make sense? And again, you can just do some English translation of this, right? You see, it is not the case that both P and Q are true. It's basically saying either P is not true or Q is not true, right? Or it is not the case that at least one of P and Q are true. That's what OR means. That means neither P is true nor Q is true, right? So it's an AND of not P and not Q. Okay? So the universal quantifier, I told you that you can think of it as a grand AND conjunction of the predicate value for each element of the universe of discourse, right? Assuming the universe of discourse is finite. So if the universe of discourse is, let's say, 1, 2, 3, 4, 5, n, we are talking about numbers, positive integers between 1 and n, we are talking about them. So then, and for all x p of x, basically I want to say that p of 1 is true, and p of 2 is true, and p of 3 is true, and p of 4 is true, right? And so on up to p of n is true. Is this clear? This analogy clear? This kind of way of thinking about a universal quantifier, when the universe of discourse is finite, we can think of it like this, right? Now, what is the negation of for all x p of x? If I made this big ANDed statement, what will be the negative of it? What will be the negative of it if I make this big AND statement?
Sir, one of them can be 0, false.
Sorry, say it again.
Sir, I'm trying to say that all of it is like a universal AND between all possible inputs.
This red statement is, yes.
So if even one of them is false, so that
Yeah.
means like at least one.
Yes, please say it again.
Not P1 or not P2.
Yeah, that's a good way. Even earlier than that, it's a good way. I'll come to that. We are saying P1 is true, and P2 is true, and P4 is true, and P3. I'm basically all of P's are true for P is true for all numbers between 1 and n. If I want to negate it, I will say yes.
There exists an S
Yeah.
and X for which P of X is false.
Yeah, I will say that at least one of these n numbers, for at least one of these n numbers, P is false. That will be the negative of this, right? For at least one of them, and that's an existentially quantified statement, right? That's why the negation of for all x p of x can be thought of as the negation of this long-ended expression, and apply the De Morgan's law to this. The De Morgan's law say it will be not P of f1 or not P of 2 or not P of 3 or so on, right? And or can be thought of as an essentially quantified statement, right? At least one of, for at least one x p is false, x between 1 and n, okay? Similarly, the other side we discussed last time. I'm going to go through this quickly because we are beginning that nested quantifier. Remember this thing, okay? Negation of quantified statement works as follows. This is algorithmically, that's how in our schools mathematics is taught. The algorithm of mathematics, don't do that, don't learn it like this, but use it like this, okay? You know the concept. Generally speaking, when you have the negation of a universally quantified statement or any quantified statement, the negation goes inside and the quantifier flips. Okay, that's the De Morgan's law. That's how I remember or understand the De Morgan's law. Okay, here is a summary of this whole thing. When is for all x p of x true? For all x p of x is true. When can one by one please tell me when is for all x p of x true? Yes, you. When is for all x p of x true? Quickly, yes.
P of x is true for all values of x.
When p of x is actually true for all possible values of x or for all values of x within the universe of discourse, right? When is p of x or for all x p of x false? When is for all x p of x false? When is this statement false? There exists one x. There exists x, one x, not p of x, roughly the correct statement. Yes, please. When p, the property, the predicate is false for at least one element of the universe of discourse, right? For one or more, for at least one or more element, for at least one or more x's, p is false, then this is false, right? Similarly, when is there exist x p of x true? When is there exist x p of x true?
When there's an x,
Yes, quickly.
there's an x for which p exists.
When there is an x for which p is true, okay, at least one x true, one or more x for which p. When is there exist x p of x false? Yes, and less, quickly.
When it's false for all values of x. When p of x is false for all values of x.
Yes, when p is false for every value of x, right? And when is the negation of there exist x p of x false? True? When is the negation of there exist?
P of x is false for all x.
When p of x is actually false for all x, then
Not p of x is not
there exist. Not there exists x, p of x is true when p is actually false for all values of x, right? All possible values of x. And when is there the negation of not there exist x p of x true, false? When is not there exist x p of x false?
when there is an x for which p of x is true. At least
When p, because this one says for none does not exist a single x for which p is true. This statement will be false when there does exist a x for which p is true, right? And similarly, the negation of for all x p of x, when is it true? When is the negation of for all x p of x true? You didn't answer my earlier question, quickly.
when there is one x, at least one x for which p of x is true.
If there is at least one x for which p of x is true? Yes, this negation of not for all x p of x, when is this true?
It is true when there is at least.
Yes, go ahead, it's okay. You see this, every single one of you, I would seriously doubt if anyone cannot or does not understand this, right? Your clarity of thoughts, it's a language course, it's a language concept. The clarity will come from the clarity of your language. So that's what I told you earlier. Make up a story, give proper, clear, precise, unambiguous words to these concepts and say it like this, right? When is not there for all x p of x true? Blue shirt, yes, quick.
P of x is true for every x.
When p of x is true for every x, does everyone agree with that? When is not for all x p of x true?
When p of x is false
For at least one x, okay? So what you said was actually true, the truth of for all x p of x. This is true when there is at least one x, one or more x's for which p is false. Then not for all x p of x is true, okay? When is it false? When is somebody said it is not the case that p is true for all x's. When will this case be false? When is this statement be false?
It's true for all x.
Even it actually is true for all x, because the claim is, the statement is, it is not the case it's true for all. And so if it's true for only one, then the statement will be false, right? Okay. Again, mouthful of words, right? No deep concept. All of you are capable and actually well versed now to do this thing, right? So if I make a statement, all people are smart, right? So P of x is the statement x is smart, is the predicate x is smart. What is the statement all people are smart? Can you translate all people are smart into quantified predicate? For all x P of x, right? I gave you specifically, this is how we pronounce it, this is what it means. So now, can somebody else please translate this into logical expression? Yes?
For all x, p of x.
For all x P of x, right? That's how we will say this for every x, depending on who are we talking about. P of x is true, we want to say this. Is this true or false? If you want to prove this thing is false, or if you want to prove this thing is true, what will you do?
For some x, not p of x.
That will show what?
It's a counterexample.
Okay, so this if you want, this is obviously false statement. Not all people are smart, right? There are cricketers and there are other people. So this is obvious. So the way you will prove, just like I proved that this statement is false, is I gave you a counter example, right? Some people are stupid. That's actually the negation of this statement, isn't it? You see the negation? Some people are stupid. The stupid and smart, if you think of it, is the negation of each other, and all and some are actually that existential quantifier and universal quantifiers, right? This is how we negate things, right? But this example should really make it clear how do you negate quantified statements and how would you write it and how would you prove one to be true or prove it to be false and so much the other thing, right? The previous table, if you remember, you see, all you need to give us is one example here to disprove an universally quantified statement, and you need to give me one example here to prove an existentially quantified statement, right? So remember these slides, fill in the name of whoever you want. It's a cool one. At some point I was thinking, oh, who should be the counter example, and simultaneously this thing was running on TV. So she was asked, which of the following is the largest, a peanut, the moon, an elephant, or a kettle? The answer is the elephant, an elephant. Okay. Let's do one example of this thing. Which of the following is equivalent to the negation of for all x P of x? 4. Yes. Which? Sorry? 4. Anybody else? Any other idea? Which of the following is equivalent to the negation of not for all x P of x? 4, right? That's the right answer because we just say that there exists some for which P is not true. So that's the negative of that, right? Which of the following is equivalent to the negation of there exists x P of x? Not there exists x P of x. Yes? Again 4. For all x not P of x, right? So the answer is always 4. Okay. Let me just do this one thing. It's an ICP. We're going to do it, and the rest, the next slide stuff is going to be for your practice. All students in CS410 are CS major, right? So I don't know what is CS410, but I just wanted to write a course with a 400 level CS code, assuming CS majors are going to, only CS majors are going to take that course, right? So if I want to say all students in CS410 are CS major, that's a statement. I want to say, the question is, negate it in English, right? Now, don't use the way we derive a negation. It is not the case that all students in CS410 are CS major, right? Plain, easy, simple, fewer words, English translation. Yes, please. Okay. Anyone else? Yes, if you want to negate this statement. Not all students in CS410 are CS major. Good.
Some students in CS410 are not CS.
Some. Anybody else? Yes, please.
There is at least one student in CS410 that is not.
Who is not a CS major? I hope you heard all of them. Some students in CS410 are not a CS major. at least one is not a CS major in CS410, and not all students are CS410 major. That sounds to be, some student is generally the way I would. Yes, please. No, that's what we have been talking. That's a totally wrong translation. Okay. Suppose I assume, for the sake of argument, please listen to this. It's a good perhaps review of what we've covered so far. If I say no student in CS410 are CS major, that basically means that CS410 is not for CS people, right? Nobody. Let's say 100 students in CS410. No student in CS410 or CS major means how many CS majors are there in CS410? 0, right? This statement says, by this statement, how many students are CS major in CS410? The blue statement, not all. There are 100 students. Give me a number. 100 students, right? When you say it is not 100, doesn't mean it's 0. What if 99 students are CS major, but one is not CS major? Got it? So this at least one student or some student are not CS major. So you are right in the sense that 0 students not CS major is also included in the negation, but that is not the negation, right? It's one case that it's the opposite of this thing. There are many ways that this statement there are many cases in which this statement is not true. Only one case has 0 student CS410 major, 99 students non-CS major, CS major, 49 students CS major, 48 students CS major. All of them are cases where this will be true. Okay, or you can do that other analysis that I showed you earlier. You may have to make the negation has to be false when this is true and true when this is false. Both cannot be simultaneously true. If there are 50 students in the class who are CS major and 50 students who are not CS major, both your statement that no student is CS major and my statement that all students are CS major are simultaneously false. Cannot be negation of each other. Yes. Sorry, let me just please repeat and then I will come back to your question again. I didn't hear properly. I didn't say there are many ways we can negate this. There's only one way you can negate this. There are many ways this can be false. That's what I said. Okay. The negative is a one special statement which has to be true exactly when. Now, do you have any other question? No. Okay. Yes, please.
So, Abhigati, you prefer saying some instead of at least one. Some can there at least one or more?
Yeah. I said at least one is as good a negation of this statement. At least one idiot is not CS major is as good as some idiot is not CS major, right? That's all. Both are okay. Sorry for those. Yeah.
Some can there included at least one.
Yes, some is at least one, and some are actually synonymous, no?
Some is one.
Some में one नहीं होता.
Some two are also multiple.
I don't know. So what I don't know. This English has this issue. Some means non-zero. Some means non-zero. At least one means greater than or equal to 1, right? So I think that's, yeah, okay. So in English we'll translate it like this: at least one student is not a CS major, right? Or in CS410. Now express this next blue statement, this negation in quantifier. This one, the one at least. So let's see what am I doing here. I'm just giving you a practice with this thing. Let's say express the first statement, the first blue statement in a quantifier logical expression. If the universe of discourse is people in CS410, right? What will be this? In P is a predicate. C is a predicate, C of x means x is a CS major. Can you say please the blue statement?
There exists.
No, this one.
All students in CS410 are CS major.
Yeah, logical expression.
For all x.
For all x in the universe of discourse, P is true, P of x is true, right? That's what we will say. So universe of discourse, okay, for all x, C of x. So I meant the first statement, okay, from this. I'm just going to give you further practice with why does it make sense to negate things a certain way. Now negate the quantified statement with no, now negate this thing how do we negate this? What is the negation of for all x p of x? Yes.
At least one,
Say it in a logical expression, please.
there exists x for not C of x.
Yeah, there exists an x such that not c of x, right? Such that not c of x is true. Yes, please.
For some x, not C.
No, in logical expression. Okay, so logical quantified expression, you have to do this. This is how we'll do it. We saw it many times. Now let's translate this quantified expression into English. Can you please say this statement? Yes, you. There exists some x.
There is some x in CS410 but not in CS.
Yeah, there is some x in CS410. That's a good thing because the universe of discourse is CS410. There exists an x in CS410 for which not c of x is true, meaning for who is not a CS major, right? Now, if you look at this and this our plain English to English negation, does it make sense? Are they the same, right? There is a student, at least one student in CS410. I forgot that there in CS410 is not a CS. Right? If you compare, they are actually equivalent. That's how you do translation initially. When you're not, if you feel like you're making mistake or something, please do this step by step. See this comparison in like 10 minutes. You should be well versed with this, right? And you should not make any mistakes. Do practice with these questions, and there are other statements. It's exactly the same 5 tasks, and they will actually give you a good practice of this. Okay, so this is a very good important topic, slightly expanded language, which is more close to our, going to be close to our needs in computer science, in engineering, in sciences, and in real life. So we'll be able to make more complex statement in this language now, okay? And that is nested quantifier. Remember in programming, you learn iterations, loops, and then the next thing, what's the next thing after loops? Nested loops, right? Loops within a loop. Loop is just a piece of code. Why can't I run a piece of code multiple times, right? I can iterate, or I can iterate on any piece of code. That code by itself could be made in, it could be an iterative piece of code. That's exactly a statement. I can make a statement about. So because we just discussed it, I'm not going to give you a review of those things. We know that predicates could be just like other functions. Could have one or more variables. Propositional function could also have more than one variables, right? And so these are the examples we discussed. P of x is a one variable. P of xy is a two variable predicate. If it stands for x teaches course y in LUMSx. Q of xyz has three variables. Let's say it stands for x is an instructor of course y in some university z. Right, so we'll just fill in the values of the variable and it will become either true or false, right? So it's a three variables predicate. Here is another three variables predicate s. I call it s. The sum of x plus y is equal to z, right? So is s1, 2, 3 true? What is the value of s1, 2, 3? What is the statement s1, 2, 3? Yeah. What is s3, 2, 1? What is the statement S321? What is the statement, not the truth value? 3 plus 2 equals 1, right? So when I give values to the variables, it becomes either true or false, and it becomes a proposition, okay? So each variable needs to be given a value in order for this predicate to become a proposition, okay? Each of them. So for example, if I ask you, is S123, is it true? Yes? S213, is it true? S213 is not true? It's true. S312, is it true? True? False. S31Z, is it true? S12Z. It's not a proposition yet. Why is it not a proposition? Z doesn't have a value, right? So, and I said we don't have to just give it one specific value. We could talk about it in the range of values, right, using a quantifiers. So if I say for all x p of xy, Is that a proposition? It's not a proposition, because in this case we say y is free, y is a free variable, right? Y is not bound. X is bound, x got a value or range of values, x now is bound to have some values in the universe of discourse, in this case all of them, right? Y is a free variable, it's unbound, it's not yet bound, right? So we need to bind it. Yes, please.
So what do you mean? So much here, is it bound or free?
So I'm just using a word here, not very thing. So we fixed, so the value of x is fixed here, right? If the value of x is fixed, right, not of one value, but at least the range or a set is there, right? That's why I didn't use the word fixed there. The value of x is somehow known, but what is the value of y? We don't know, right? It's not, we are not told anything about it, so you can't ask me that was it true or false. It's not a proposition yet, okay? So it's the concept of binding variable. If I make this statement for all x, for all y, p of xy, remember, it's a two-dimensional variable, right? A two-dimensional predicate, a two variable predicate, right? I have to give value fixed to x and y, some value or range of values. I have to quantify both x and y. Okay, maybe a better word would be, instead of bound, you could perhaps say quantified. X is quantified in the previous one, y isn't quantified, right? Y isn't given value, now it's bound. I haven't seen quantified as such, so but generally in the literature it's called bound. Here both x and y are bound, right? So depending on what is actually P stands for, what is the sentence P, and what's the universe of discourse, it may be true or may be false, right? We don't know. But here both variables are bound, right? Or both variables are quantified. Here there are three variable predicate, q, x, y, z, whatever q stands for. I've quantified x, I've quantified y, I've quantified z. So all three variables are bound. Now it's a valid statement, it's a valid proposition. I can ask whether it's true or false, right? So we're going to talk about, this is what is called nesting quantifier. You see this quantifier, this whole statement, is this statement a proposition? It is a proposition because z is bound and x and y are also quantified. So this whole thing is like nesting these quantifiers one after the other, loops, right? If things. So I'm going to give you examples. Yes.
Sir, we don't know the universe of discourse yet, so we can't call them quantifiers.
Yeah, we don't even know what is q. We don't even know what is q. But this is just a very syntactic example. Okay. Now, if I ask you whether this thing on the left side is a quantified expression, nested quantified, two variables, so two quantifiers. On the right side also two variables and two quantifiers. I'm asking, are they equal, right? It depends on P and it depends on this thing, but there is some kind of a compile time error in this statement. What is that? Look at the left hand side. The left, yes please.
Sir, they're not yet propositions.
They are not yet propositions.
Because on the right hand side, x is bound in one and y is bound in the other.
Yes please.
Right-hand side proposition.
Yeah, on the left hand side we have a proposition because both x and y are bound. On the right hand side we seem to be taking and of two things, but and we defined only for propositions, right? Compound proposition is made up of atomic proposition. But the two constituent anded things are not actually proposition. This isn't a proposition. Why? The first term in the right hand side is unbound. The first term, this is a whole term. Here y is not bound, so it's not a proposition, right? So you can't take and with something. It's just, you can just type it in, but there is a grammatical mistake in this statement, right? This is not even a statement. You can't take and of two non-propositions. You can't take and of x, and of Ahmad with y is bigger than 3. We need y is bigger than 3 or 4 is bigger than 3 is a proposition, but Ahmad isn't a proposition. You can't take and of them, right? So and has to be done between two propositions. So here the left hand side is good. It's both x and y are bound, so it's kind of a proposition. The right hand side, the first term in the first term, in the first predicate, it's actually x is bound, y isn't bound, and in the second predicate, y is bound and x is free or something. So RHS is not even a proposition, right? So we can't just ask this question whether they are equal or not. Yes, please.
So the right hand पे दोनों terms unbound होती, bound होती तो फिर हम
Bound hoti, then it's a valid question. We don't know the answer because it depends on P and the universe of discourse and other stuff, but then it will become a different story. So we're going to talk about nested quantified expression, right? Quantified expression, which are the predicates involved have more than one variable, two or more variables, and both variables need to have some kind of quantification and something. Okay. Remember the Goldbach conjecture? And I told you then that wait for a while, that it's not really proposition, but I wanted to make a point then. So this is actually the Goldbach conjecture. Can somebody please say this thing? There is an English thing, and then there is a math translation of this. Yeah. Can you just say the math word in English?
For all n that belongs to the natural number.
For every natural number, that's how generally we say this thing. It's okay, you begin with this thing for all n that belongs to natural numbers, but that's not how we generally pronounce it, right? You will learn to do this without this intermediate step, but okay, go ahead.
N greater than 2, which is also even, it implies that there exists a P and Q that Q belongs to the set P.
The set P stands for prime numbers. We'll talk about this later.
For which n is equals to P plus Q.
Anybody else? Yes, please. So I want your own attempts, because I've given you the English translation, right? The correct translation, we talked about it earlier. This is really but I just really want to do this one intermediate step for you. Do this and then see why does it make sense. Yes, please go ahead. There exist two P and Q from P, which are prime numbers, such that n can be written as P. Now read to yourself the English translation, or the, when it's actually the math is, I wrote the math as a translation of the English because it came first. But I want you to really appreciate that these two are exactly the same thing. Every even integer word is here. Every is for all. Integer is natural number, right? Even is an even. Greater than 2 is greater than 2. So even greater than 2 integer, this is like an AND of two things, right? Even and greater than 2 is the AND. Every can be is this, there exist, right? Can be means there is a possibility, there is a choice of doing this, achieving this thing, right? Can be written. So there exists P and Q. Right now you are not familiar with this. I made a technical mistake here. There should be there exists P, there exists Q, but when there is the same quantifier, we try to write there exists P and there exists Q. Shorthand notation, there exists P and Q, right? But such that number n can be written as P plus Q. And P and Q are prime. R prime is they are in the set of prime numbers, right? Is this clear? This is the kind of statements we are going to learn to make, right? This is an example. Next, please. N is even. No, n is even. Mathematically, कैसा लिखता है वो, there are ways to write it, and we will write it later. But right now, just want to say n is even. Let me just do that. So, okay, you want to. How would you write n is even? How would you write n is even in a predicate? It's a very good question. Please, you guys, please pay attention to me. How would you write n is even?
n% 2 double equal to 0%.
What is percentage? Come on. Well, how do you define even? How do you define even to a kindergarten student? You will tell remainder to a kindergarten student? Yes, a multiple of, how do you define multiples of 2? How you define multiples of 2?
N is equals to 2p for p belongs to.
Yeah, so here is how I would write an n is even. This is the English number. There exists a k among the integers, right, such that n is equal to 2 times k. That make sense? That's a quantified statement, so I thought it was relevant to you. This is one quantifier. There exists k such that n is equal to 2k. Is this clear? Yes? K has to be an integer, because if k is 1.5, then 3 is equal to 2 times 1.5, right? So we don't want 1.5. Okay, good question actually. Yeah. Yes, there is speak. Forget about that. That's for the technicality. You don't need to worry about this. Vinogradov theorem. I think we talked about it or not, but it's a kind of an extension of the Goldbach conjecture. People couldn't prove Goldbach conjecture, so they tried to prove similar statements, right? So Vinogradov proved that every odd integers, which is big enough, sufficiently large odd number, can be written as a sum of 3 primes, right? Quite old and quite good, it's a solid result. So, but I just wanted to bring this sufficiently large odd integer, right? So even sum of 2 primes, sum of 3 primes, integers, primes, everything you can. The only thing different in this and the previous statement, well, one is not known yet to be true or false. It's still a conjecture. This one is a theorem. We know it's true. But I wanted to bring it for you, the difference is this sufficiently large. How do you say something like sufficiently large? Here we say exactly greater than 2. Not large, larger than 2, but the sufficiently large seems very vague there, right? So in math, how you write that? Yes?
So you could say that for some x that belongs to the natural numbers, as long as we are greater than that.
Yeah, so there is a bound, a lower bound on this. But the statement is like this. There exists a lower bound, there exists a starting point k such that any number that is bigger than k, that k there is 2, right? But there is known to be 2. Here we say there exists some, we don't know which one. So the one doesn't need to be very precise in every statement, right? For sufficiently large k, there exists some k such that whenever n is bigger than k and n is odd you can write exactly those way, and n is odd, then n can be written, there are 3 primes p, q and r such that n can be written as sum of the 3 prime number p plus q plus r, right? Forget about it, that's don't worry. Okay, let's do some easier examples, our level stuff. Suppose I want to write the sum of 2 positive integers is always positive. Try to stay within English, but try to write it, say it more differently, or just play with this thing so it will become simple and precise, more precise in something. How would you write it? So there is this hint there, sum of any 2 positive integers, sum of every pair of positive integers, so that should give you some for all types of.
For all x greater than 0, y greater than 0, z is equal to x plus 1.
What is x equal to?
The sum is n or z, which is
Okay, is
like what? Like
greater than 0, yes. Green shirt, what are you saying, something?
For all p and q greater than 0, p plus q is greater.
Good. For all p and for all q, if p and q are bigger than 0, then p plus q is also bigger than 0, right? So look at this translation. Well, pq, because we just said primes, for all x and for all y. If x and y are bigger than 0, if x is bigger than 0 and y is bigger than 0, that's where the positive integer, every 2 positive integer comes, then x plus y is bigger than 0, right? Now I don't write universe of discourse in something, we never said in Z, let's say the universe of discourse is integers. If it's positive integers, you don't even need this condition, right? If the universe of discourse is integers, I need to say any x and any y in this set, as long as they have this one property that x is bigger than 0, positive, it's integer, so it can 3.5 is not out of the question, right? So there is a, and y is bigger than 0, then x plus y is also bigger than 0. Make sense? Okay. There could be many ways to translate it, and many ways to be increase. There is a more deeper and deeper level of precision that you can do, but that's my attempt to do this thing and try your own. Every real number except 0 has a multiplicative inverse. Every real number bigger than 0 has a multiplicand, not bigger than 0, non-zero. Every non-zero real number has a multiplicative inverse. How would you write that? Quickly. Every non-zero real number has a multiplicative inverse. Yes?
For all x where x is greater than 0, it implies that x times the negation of x is equal to 1.
What is the negation of x? What is the negation of x?
Sorry, x divided by x is equal to 1.
Yes, so the reciprocal of x. Yeah. Yes.
For all x not equal to 0 and for all y 1 over x, x times 1 over x, 1 over y, x
Okay.
times y, sorry, because y.
X times y is equal. Okay. So the way I wrote it is this thing. For all x, there exists a y such that if x is bigger than 0, then y, x times y is equal to 1. Let me just answer the question first, and then we will begin the others. The question is a very good question. It says that why didn't I specify where is this x and y coming from, right? Where the x and y and whatever these numbers are. In the previous one, I didn't say where x and y are coming from, right? So if you remember, I told you earlier that the universe of discourse is a very important concept. You have to be clear about it. If you think there could be confusion, you have to explicitly state it, right? But if you think the things are going to be clear from the context, or the only thing we are talking about is that subset, then you don't really need to explicitly state it. So for example, when I say all students are CS majors, all students in CS210 are students major, I didn't say the universe of discourse was LUMSx student. I didn't explicitly state that, right? But because CS major is a LUMSx concept, CS210 is a LUMSx course, let's say, and so it was clear from the context of what we were talking about, right? Does this make sense? That's why I didn't say specifically, I didn't specify specifically what was where are they coming from, right? Or if you really want, or maybe I will do it in the slides, I'll add this thing that the universe of discourse for x and y is this set. Okay?
Could we translate this as for all x, for which x is not equal to 0, x multiplied by 1 over x is equal to 0?
Yes, that's you can do that. X times 1 over x is 0. But then what is this 1 over x? One has to know that 1 over x is also a definition, but that's what exactly y is equal to 1 over x. There exists some number. So why can't I do it for 0? If you say this thing, why do you have to add the condition x is not equal to 0? Because 1 over 0 is nothing, is not known, it's not a real number. We want to say there exists a real number. If you really want to know, if you really want to do it, if you want to define it, your own rules of mathematics, you can say that 1 over 0 is equal to 1, right? Or 1 over 0 is equal to 0, or whatever you want to say. Just say this 1 over 0 is equal to 1, 0 times 1 is 1, right? So you got yourself an inverse of that. So you just want to say that for every x that is not 0, there is another real number. There is a real number, not another. For 1, the inverse is also 1, right? The reciprocal is 1. For every real number, there is a real number which when multiplied with this number gives me 0. Okay? I'm going to give you the same example later. There will be some perhaps universe of discourse and some other relevant examples. Okay, just want to tell you the quantification of two variables differently or same or something, right, but nested quantifier. You see in all of these statements there are at least two quantifiers appearing, right? Yes, do you see two quantifiers here? Do you see two quantifiers here? Which two? Yeah, how many quantifiers are in the first blue statement? Which ones? Both variables are universally quantified for all, right? And the next one is, the first one is universal, the second one is existential. Okay, if a person is female and that person is a parent, then this person must be the mother of someone. Okay. I want you to use two quantifiers. If a person, every person who is female and who is a parent, then this someone, what is this someone? There will be, there exists, right? There exists a child of this person then. Does that make sense? It's the mother of someone. There exists someone for whom this person is a mother, right? So again, wanted to use two quantifier, at least two quantifier. For all x, there exists y such that if f of x, now f suppose is the predicate that f is a female, x is a female, f of x stands for x is a female, and p of x stands for x is a parent. Okay, if x is a female and x is a parent, then now go to there exists y, there exists someone to whom this x, there exists some y to whom x is a mother, right? So mxy means x is the mother of y. Yes, please. Later we will see that we learn when we have practice, we can write it wherever you want, as long as it comes before this y. If you use it after this y, then this y here will just not compile, right? This will not, it's an unbound variable.
That means the position is not like fixed for those quantifiers.
Let's just give it a minute, okay? Its position is, its order is fixed, we'll see what happens. Yes, please. That's yes, y. So there is someone to whom x is a mother. So there exists a child. If x says I'm a parent, then there exists a child, right? Of x. So that's what it says.
So mx or y?
Mxy stands for x is the mother of y. The first variable, the first person in this statement is the mother of the second variable, the second person. Yes, please.
If we make the universe of discourse then we can remove more and more qualifiers.
If we remove the universe of discourse,
If we make the universe of discourse more specific, if we say we're only talking about students, so the qualifier.
that's a very good way. If you make, let's say, suppose here I assume the universe of discourse is all people, right? If we make, let's say, the universe of discourse all women, all female, then we don't need to test this thing because it's already true, right? This condition is already true. We are only talking about female. So if x is a female is trivially true. So why do you even write it? Right? Yes, please.
I had a question like, for there exists a y if we take it to the other side of the implication sign. So that would also be true in that case.
It should be, it's not a good style that you first talk about the variable and then you write the body of the statement. But technically, yes, you can do it, and we will be using it when we, like last time I did it actually. If you see here, we did it here, right? So here we, because now this is a mature statement. I kind of, because we used it earlier, that's why I mentioned it here. But there was, generally speaking, we write more technically correct, strictly correct statement is first get rid of all the variables, but be very careful. You can make many mistakes. That's why it's sometimes good idea to write it when later on you can write it in the wherever you first time you need. Yes.
If the next slide is, if we do we not
We don't want to satisfy, good.
We need to specify कि y 0 नहीं हो सकता. Where is that problem?
0 क्या नहीं होता इधर? No. No, so give me x, any x who is not 0, there is some y. There is some y. So I said there is some y. Why do I have to say y 0 नहीं हो सकता? Look at the claim, look at the claim. Every non-zero number has a inverse. I'm not going to give you the value of the inverse, there is someone. So there is someone, I don't have to give you the inverse, right? I mean, this is not a, it is a claim that we make. It's not a kind of a test that, okay, what is the inverse of 13? What's the inverse of 4.7? What's the inverse of -3? That's not going to be the case, right? Every number has an inverse, a linguistic claim. I made a claim in this language, and that's how I write the claim, right? Yeah.
Second, could you go to the next one for a second? So, like someone said that if we limited the universal discourse to just women, then we could get rid of the first
condition, perhaps.
But that would also have other consequences. For example, then this wouldn't always be true because
that's good. So, it's a very good question, very good thing. So, he's adding to your thing. What if we change the universe of discourse for to women only? Then it will be just say daughters, right? The Y will also. So, but I think what she meant, or definitely what I meant, two variables could have different universes of discourse. So, if for X the universe of discourse is females or women, then and for Y the universe of discourse is all people, then I don't need to, I will still be able to get rid of f of x, but if you're right, if I said the universe of discourse for x is all women and the universe of discourse for y is all women, the statement may not be true, right? Because then this statement would be true. This statement would translate back to English. If a person is female and is also a parent, then this person is some girl's mother, right? So this person then has some girl's mother, because if my universe of discourse is all women, then this y cannot take the value of a boy, right? Okay, everyone has exactly one best friend. Okay, everyone has one, that's for all, at least one would be there exist. Now there is exactly one, right? So you have to somehow take care of this exactly one also. Otherwise, if everybody has at least one friend, how would you write that? So everybody, now I know we are talking about people, we are not talking about numbers, right? Now for every x, there exists a y such that x and y are best friends, right? Such that bxy or fxy, whatever you want to shorthand it, such that x and y are best friend, or y is the best friend of x, right? But that translates to, if I translate it back to English, it translates to everybody has at least one best friend, or there is no one who has no best friend, or that type. This one says exactly one best friend. So we need to further qualify it, right? We need to further restrict. If you say y equals 1, this just is a compile time error, because what is the universe of discourse for y? What type of values can y take? Ahmad, Fatima, whatever, right? This type of, that's the value of y. Now you say y equals 1, that's just is a, I mean seriously, these you guys should be, this is the type of statement that you should worry about it, right? This is a very, very bad mistake. I mean I wouldn't be surprised if you make such statements after a few classes. Look at this statement. For every x there exists y such that b of xy, b means x and y are best friend, or y is the best friend of x, depending on how do you, if it's a bidirectional friendship or this one-sided friendship or whatever type stuff, right? B of xy means x is the best friend of y, right? For every x there exists a y such that y is the best friend of x, right? That's the sum, at least one best friend type thing. But then it also says, and y is not equal to z. If you take any other z, then z is not a best friend of x. That makes sense? If you translate it back to English, it will become a mess. everybody has at least one friend, and if I check any other person other than y, that is not the best friend, right? Yes?
सर अगर हम इसमें से y equals to z कर दें और negation को खत्म कर दें, negates best friend x and z, so it will be for all values of x there exists a y, and for all values of z such that the best friend of x and y is such y is equals to z.
Okay, so slightly you're getting off topic, but you can, if you really hate the this inequality sign, you can convert it to equality sign by perhaps doing something like this. For all x there exists y such that b of xy. So far we are happy, right? Everybody has at least one friend. For every x there is at least one friend, right? And for all z, if z is also best friend of x, then y is equal to z. But if you really think about it, I just took the contrapositive of this implication and gave you not b, not of not b, and not of inequality, right? This is generally mathematician would write it like this. If somebody else claimed to be a best friend, that must be y themselves, right? There is no one else. Okay? Again, don't worry about this technicality. I will say quantifier can have multiple variables, right? Each variable needs to be quantified. Okay. Now this is a really important. This stuff is coming, and that's true. We'll go back to a lot of examples we have there. Translate this into English. F of xy means friends. X and y are friends. Okay. Suppose f of xy means x and y are friends, and the universe of discourse is all people. Translate this statement.
Everyone has a friend who is not them.
Everyone has some friend, some other guy as friend, right?
Everyone has at least one friend that is not themselves.
Yeah, so in English we don't explicitly say not themselves, right? But I can say everybody is a friend of itself, so that's why the statement is trivially true. But when we mean that everybody has someone else's friends, right? Everybody has someone else his friend, at least one friend other than himself, right? Herself. It's clear? You see, everyone is at least one other friend. Okay. Okay, this one. There exists a y for all x, f of xy, and x is not equal to y. This is f of xy still stands for x and y are best friend, or x and y are friends, or y is friend of x. How does you pronounce this? Please pay attention to this, okay? This is the most important takeaway from this today's lecture. Yes?
Someone is friends with everyone.
Yes, please. Do you want to say something? Green shirt. Same as what? Can you translate it into English? Why everyone is a friend? Where is this everyone coming from? For all x, okay. Yes. So now can you please translate it word by word? Go from here. How do you pronounce it in English? There exists a y.
There exists a y such that for all x,
X and y are friend. Is it the same as this blue statement? Okay, just hold on to your thoughts, okay? Yes.
Everybody is friends with at least one person.
How do you come from here? This everybody is at least.
Y, such that for all x, everybody can remember x को universally quantify करते हैं.
Yes.
So everybody is at least friends with one person.
No, but this at least, where the at least coming first, or the everybody comes first? Where is everybody coming from? Everybody is second statement. Function, no, x and y are friends. The function are fxy is the same as fyx, let's say. Start the sentence from here. in order translation, yes, but we'll come to that.
There is at least one person who is friends with everyone.
There is at least one person, there exists a person, at least one person, that's there exists y, such that for all x's, other x's, let's say for all other people, that person is a friend with. Right? Yes, somebody raised hand here? No? Someone has everyone x as every other person as a friend. Yes?
So the question which is at least someone is everyone's friend. Is that
Yeah.
right?
So is it the same? That's roughly right. Is it the same as the blue statement? This is the translation. There is at least one person who is friend with everyone. Right? The other one is everyone is friend with at least one friend, at least one other person. This one says there is at least one person who is friend with everyone, every other ones. Are they the same statements?
They are not the same. Second to be true, the first has to be true.
Forget about true or false thing. Are they the same statements? Can you give me any other example of this thing? Any other example? So every course has a teacher, right? Every teacher has a course. Are they the same?
No.
Why not?
There could be multiple courses.
But they're different statements, right? Okay, yes. Wanted to say something? They're totally different statements, right? So that's what we'll talk about it. And somebody was saying something, and I said, okay, this is going to be our main thing for now onward. Yes.
जो आपकी जो example थी, isn't that an implication? Like every course has a teacher, पर ये इसमें implication नहीं होगी, इसमें दूसरी चीज़ है.
I don't know what is implication coming here. It's exactly the same. Say x teaches y. If you plug in f x y to be x teaches y, then where is implication
But
coming
the thing
from?
is, जैसे x है ना, तो वो imply कर रहा है कि like y को teach कर रहा है, और इसमें
Okay, let's just do a few more, and then we'll discuss it in more detail. What is this statement? For all x, there exists y such that if x is not 0, then x times y is equal to 1. Translated into English.
Every number greater than 0 has a multiple.
Greater than 0? Where is greater than 0 coming from?
Every non-zero number.
Every non-zero number has a multiplicative inverse, right? We discussed it, and it's going to come even later again. Again, the universe of discourse, don't worry about that, it's real numbers. If I say this statement, what is this statement? Please translate it. Exactly the same statement, the quantifiers are written differently. There exists a number y such that for all non-zero numbers, x times y is equal to 1. So how would you easily translate it?
There exists a number y for all non-zero x is the multiplicative inverse of x.
Yeah, so even simpler English.
there exists a multiplicative inverse for every real number except 0.
That's exactly the previous statement.
There is a number y which is multiplicative inverse of
Everyone. That's, yes.
There exists such a y that its product of each x results in 1.
Yeah.
All non-zero values of x have the same multiplicative inverse.
Roughly the same. We didn't say the same, but yes.
There is a universal multiplicative inverse.
Yeah, other than 0. So all of this, you see, the first statement says every number has a inverse. The next one says there is one inverse, there is one number who works as inverse of every number. Are they different statements? Are they different statements? Right? Now, similarly, the previous one, everybody has at least one friend, and the other one was this one person who is friend with everyone. These are totally different statements, right? Maybe both true, maybe both false. That's a different story, right? This one is obviously false. There is no number that when multiplied with anything will give you 1, right? That's just not true about based on our understanding of mathematics. For 2, only half gives me, when the product of 2 and half is 1. There is no other number which in product with 2 will give me 1. And similarly, half will give me, half is the inverse of 2. It's not the inverse of 2.5 or 2.7, right? It's not the inverse of 4. So, the two are very different statements. Okay? So, the conclusion is, this is one thing that you really have to understand. For all x there exists a y, p of xy is not the same as there exists x for all y, there exists y for all x, p of xy. If you flip the order of the quantifier and the variables, you do get a different statement. Maybe true, maybe false, that's a different thing. The statements are different, they are not the same statements. Is this clear? With the previous examples, it should be clear, and I'm going to give you a few more. So let's say p of xy, x teaches course y and x. Let's assume every course has a teacher, otherwise an instructor, right? Otherwise it won't be a course, right? A course is defined to have a course, an instructor and a bunch of students, and there are course outline and content and some kind of assessment. That's the basic stuff about. Now, if I make this statement, for all x, x is the teacher, x is the set of people, the universe of discourse is set of people in LUMS or set of LUMS faculty, or right, y is set of, the y universe of discourse is set of courses listed on Zambil or something, right. For all x, there exists y p of xy. How would you translate it? Just plug in the value of p and maybe the universe of discourses. Yes.
So for all teachers that teach some course.
Yes.
So all courses have at least one professor.
Here is all courses. How do you say all courses first? What is this written here? Every person. X, the universe of discourse is people. Y, the universe of discourse is courses. Say it again now.
All courses have.
Again, all courses is not there. This all is for X, for people. Every faculty member teaches at least one course. That's how we translate it, right? True or false, it's a separate story, right? Maybe somebody is on sabbatical. Maybe somebody taught 19 courses last semester, is not teaching any, right? Maybe somebody is dead or whatever, right? So this is something. For every instructor, there is a course that he or she teaches, right? That's kind of the translation. Okay, let's flip the order. The universe of discourse for Y is courses. The universe of discourse for X is LUMS faculty. Can you please translate it? Yes.
At least one course and all the teachers are LUMSx.
Can you please translate this thing? What happened? Okay. Yes.
There are some courses which every instructor teaches.
There is a course that all of the faculty or every member of faculty teaches. Yes? That's what is written there on the board. Are these the same statements? Right? What is the difference? What is the difference between these two? What's the difference between these two statements? Just look at the face value. What is the difference? The order of quantifier has been flipped, right? The statement becomes very different. Maybe both true, maybe both false. Maybe there is a universal course that everybody has to teach, right? There should be, but that be course, but it's a different statement, right? These two statements are very different, okay? There exists a teacher. Every teacher has at least one course, otherwise you're just sitting useless, right? Getting haram salary, I guess, right? Or and this one says there is a course that's so popular or so important or so fundamental that everybody has to teach. That's a different statement, right? Again, truth, false, truth value is a different story. Okay. Now, if I say this thing, there exists x for all y p of xy. What is this statement? Again, x, the universe of discourse is all people, y, the universe of discourse is there exists Yes.
So there exists a teacher which is all courses.
Yes. There exists someone who, no matter what course do I pick, that person teaches all the courses, right? Or any of the course I picked. Okay? Different statement. Most probably false on any place, any university, not just LUMS, right? Again, in some cases could be true. What if LUMS at some semester or LUMS is just beginning, right? Today is only the first MBA set of idiots coming. There is just one course, right? Business fundamentals. When in 1984 or 85, whenever this indoctrination center began, they were teaching those idiots, training them. Maybe there was the Dr. Ehsan was the first LUMS employee, right? His employee ID is 1, he just retired. Dr. Jamshed is second employee. Maybe at some point Ehsan was the only professor. They were beginning, and the LUMS had a quarter system. When I was a student at LUMS, it was a quarter system. 4 quarters a year. So in a quarter system, 1 course, 2 units, could be. So again, the truth value is a different story, but you know the statement is different. Do you understand the statement is different, right? Okay. For all y there exists x p of y, p of xy. What is this statement? For every course there is at least one instructor. Most probably true, because that's kind of the definition of a course, right? Just like here, which one was it? The first one? For every person must have a course, otherwise how do you call yourself a faculty member, right? And this one, why do you call this thing a course if it doesn't have an instructor, right? Unless there is a special types of self-taught course, this Office of Students Worshipping and this LUMS learning, people are teaching us peer learning. Maybe there is something. Again, the truth value is not our thing. But do you see these statements? You flip the order, the statement changes. Please see this board. There are these 4 possibilities of different quantifiers in different order, right? And different variables differently quantified make the statement very different, okay? And you have to be very, very careful. You need a lot of practice with this thing, okay? Okay, so here is another one. This you can just play with this thing. I'm giving you 3 things, for 3 variable quantifiers. For all z, for all y, there exists xq of xyz, right? So z is a set of universities, right? So in every university, for all courses, there is some person who teaches that. Most probably true statement, right? In every university, there must be some courses. And for every course, if we live in the world where a course has to be defined by an instructor, so then in every university, for every course, there must be some instructor, right? This statement, in every university, there is at least one person who teaches all courses, right? If in every university, there is this cruel system that one person teaches all the thousands of courses, right? That's a different statement. There exists one person. That Superman teaches all courses in all universities and does this, okay? Very different statement. Okay? Yes. Yep. Yes, please. Sorry, please say it again. The first one says in every university, for every course, there is an instructor. You go to Punjabi University, you find a list of their courses, there will be some instructor who is teaching all of these courses. You go to Lahore University, LUMS, look at the list of courses, there will be an instructor for every course. That's the first statement, right? The third statement says, there is an instructor, there is some person, X, there is Imdad, who goes to all universities and teaches all courses there. Okay? Is it different? Yeah, and most probably not true, right? Look at this statement. Keep these tables in mind, not the values in the tables, but this number of rows and number of columns. If I want to say for all rows x, for all rows there exists a column y such that a of xy is equal to 1. You should know what does it mean. This is the xth row column, the xth row and the yth column in tree, right? Is this clear? For in every row there is at least one column which is equal to 1. Okay? Is this true for table 1? Is there a 1 in at least every row? Right? So in English translation, every row has at least 1, right? This is true. Is it true for table 2? Yeah. Right? In every row, at least one entry is 1. Right? Let's flip the thing and flip the order and see. There exists column y, which is 1 for all row x. There exists a column such that every row has at least 1, 1. Every row has 1. Okay? Is it true about table 1? Do you agree with the translation? There is a column full of ones. That's what this statement says. There is column full of 1, right? Is it true about table 1? Is it true about table 2? Why is it true about table 2? Because column 1 has all ones, column 2 has all ones, column 3 has all ones. We have one example, that's good enough, right? You see the statements getting different? You see the statement getting true for one thing and not true for another thing? Dusra says there exists a column y such that for every possible value of x, a, x and y is equal to 1. I mean, no matter what value I put here, x equals 1. So the first row of y is 1, x equals 2, the second row of y is 1, the third row of y is 1, and the fourth row of y is 1. That's one magical column, right? This is what it says. There is a column which all values are 1s. And this is not true about table 1, it is true about table 2 only. Yes? If you flip the order, things change, right? Table 1 doesn't satisfy. Look at this statement. For all x, for all y, ax, y is 1. What is this statement? Can you give me a quick English translation of this statement? That's not translation, that's a pronunciation of this statement. Give me English translation of this statement, this blue statement. So let her do it. No?
Sir, your whole table has ones.
Anyone else? Sorry? Every cell is, who said? Every cell is 1. The table is full of 1, right? There is only ones in there is no empty entries or whatever way, right? Every column, every row I check is 1. So that means the table is full of 1. That's more simpler, plain English translation, right? Is it true about table 1? No. Is it true about table 2? Yes. Now let's flip the order, right? What is this statement?
The same as every cell has a 1.
Every column, every row I check is 1, meaning every cell is 1, right? Is it true about table 1? No. Is it true about table 2? Yes, it is true, right? Okay. Let's do this one. There exists x, there exists y, column x, column row x, column y such that ax, y is 1. Give me plain English translation.
There is at least one in the whole table.
There is at least a 1 in the table. The table is not empty, right? Does everybody agree with this translation? Is it true about table 1? Is it true about table 2? Yeah. Okay, let's flip the order. There exists a column y and there exists a column row x such that ax, y is 1. Give me English translation.
There is a 1.
Right? There is at least one in the table, right? Is it true about table 1? It's the same statement, so it must be the same thing, right? Yes?
Could you go back to the previous one?
Yes.
In the first blue statement, what exactly is the same?
First blue statement? This says for every row, in a more programming thing, no matter what value of x I put here and what value of y I put here, that's no matter every value of x, every possible value of y, that's coming from for all. I will get the value 1 here, right? For every possible value of x and y, ax, y is equal to 1.
So it says that for all rows and for all columns, there is at least 1.
No, where is at least 1? At least
That's what
1.
I'm trying to understand. What does the ax, y notation mean?
This AXY means the value of the table at the index X and index Y. The matrix entry X row and X row and Yth column matrix entry is 1. That's what it says. That means for all. If I put in for all. Okay. So order of quantifier is very important, right? If the quantifier is the same, we saw this here. If the quantifier is the same, I can flip the order. It doesn't make a difference. But if there are different quantifiers, then the order is extremely important, right? Okay, this is a good joke from Central Western College or something. Western Central College, North Central College in the US. So people carving pumpkins is one thing. Pumpkin carving people is a totally different story. Okay, don't give it a try. Okay, please settle down. We still have time, right? Those of you who came late should stay here. The rest will go and after a while. This is a short story of this. Please understand this table. This is going to make. This is a very important thing. Okay. This summarize one is. Let me just give you one of them. There exists X for all Y P of XY. When is this true? When is there exists X for all Y P of XY?
One X that is true for all XY.
For all Y.
There is one X which has a Y that is true everywhere in P.
Yeah, so there is an X for which Pxy is true for all Y, right? Let's say this thing. There is an X who is friend with everyone. There is a person who is friend with everyone, right? That kind of statement is true when indeed there is a person who is, this Pxy is true for every pair of, for every Y this X is paired with. Okay, and when is this statement true? When is this statement false?
There is no X for which X or Y is true for everyone.
Yeah, so I checked it for X1, at least one Y, for at least one Y, Pxy is false. Then I checked it for X2, for at least one Y, Px2y is false. Then I checked it for X3, for at least one Y, maybe different Y's for each X1, X2, X3. Px3y is false, right? So if this is not true for no X, there is, for every X there is at least one Y who, for which P of xy is not true, then this statement is false. Yes? Somebody was raising hand there? Okay, so this is the thing. I will leave these ICPs to you, for you, and then we have to negate it. Okay, maybe we'll talk a little bit about it next time.